so we have our system here. It's drawn with the mass pulley with radius r. This is radius r. Block 1 with M1, M2 with M2. The time was given to be 2.3 seconds. The height 2.5 meters. Both blocks end up traveling. So we can first start. So we'll acknowledge that down is positive. So that makes G, our constant for gravity, called constant. VOY equals 0 because they are released from rest. So the second they are released, they do not have any vertical velocity. So we start with this equation to find Vy, which then we can plug in to this equation to find A, our acceleration, and A will be useful later. Now we will move on here. So it will travel h distance when it travels t seconds. Average speed. This right here is basically the equation for average speed. So average speed times time equals displacement, which is h. So we figure out what's h, and then our equation for A, change of V, VOY. But VOY is later 0, which will not be significant in our calculations later. So later we go into here, we move this to here, we simplify it to be Vy over just Viy over t, and we simplify this to be Vy over 2 times t. Now, so after Vy over t, then this thing goes from here to here, and now we multiply both sides by 2 to get 2h. So it's basically, there's going to be a 2 here, then divided by t, and then Vy. We get our velocity Vy, which is 2h over change of time. Then we plug in, for Vy, we plug into our acceleration equation that we got earlier, and solve for Vy over t. Now we plug in Vy over t. And for A, we end up with this. So from here, we plug in 2h from the top, numerator, down already a t, but another t from here, so 2h over t. So this will be our acceleration. And now we will use the net force equation to solve for the force of tension on this T2. Solve for T2. We don't know what T2 is, but we do know what M2 and G and its acceleration is because we just solved it right here. So M2G down is positive, so this is going to be positive, negative T2. Then F equals MA. Then our M in this case would, and this is the sum of all forces. Then we take we take this, plug into here because it's F, and then F is also equal to MA, but in our case, MA is just MA, but our M is going to be M2 in this case, and the acceleration will still be A, labeled A. And solve for T2, T2, then M2 minus, factor out the M2, then we plug in our numbers that we got from the beginning and get T2. Now we want to solve for, hold on, it's distraction. Now M1 is right here, and the only net force will be from the tension because the up force, normal force, reactive force, and the force of gravity balance each other. because there's no acceleration. It's not like it's going to fly out into space. Then T1 will just equal M1A because F equals MA, and in this our case, our M is going to be M1. The tension 1 will be here, 5.1198, and so when I drew out this pulley, we realized that this pulley is unbalanced. T1 does not equal T2 because we do want some net torque. Net torque is what makes this pulley roll, and that's how these two blocks can move in the first place. So net torque is the sum of all torques. So we have this torque, we're going to make this positive torque, plus sign, negative sign, times lever arm, tension times lever arm, I alpha. A also equals alpha R. Alpha equals A over R in this case. So T2 minus R minus T1R equals IA. Both equal T. Then plug and set them equal to each other. Factor out the R. Then we're going to jump all the way down here. Now since our A alpha equals A over R is going to be here. So from here to here, this is the only difference. Now we're going to solve for I, multiply both sides by R, so R squared, and then divide both sides by A, so we get R squared. Now, because we solved everything, we solved for T2 and T1, we can now move over here to where the numbers for I will finally be plugged in. So R squared, R is 0.064 squared, R squared, times T2 minus T1. And now T2 minus T1 will just be this number we solved for here, 66.411 minus 5.198. And now here it is, divided by the acceleration. The acceleration we solve for right here, 9.945. And when we get this, we finally get our rotational inertia. Looks pretty messy, but this is my explanation. Problem 9 of the WebAssign for rotation review.